Good afternoon. This podcast is on Snell's Law. I'm Miss Mike Sell, and I'm one of the material science teachers at Eagle Crest, and I hope this podcast is helpful for you. Snell's Law looks at refraction, or the bending of light as it changes from one medium into another due to changes in optical density. So we can see this green laser light as it travels through the air is going in a perfectly straight line. But as it changes medium and enters the acrylic block, it gets bent or refracted. And then as it exits the acrylic block back into air, it's bent and refracted again. Optical density is how fast light travels through a medium relative to a vacuum. And so if two different media, like air and acrylic, have different optical densities, the light will travel at different speeds. And that change in speed is the refraction or the bending that you see of the light ray. You can see this picture on the screen taken by a spectator at a zoo of a polar bear, and the polar bear's head is in air, whereas his body is in water. The photographer, when they took the picture, it looks like an optical illusion, like the polar bear has been decapitated. But that is simply due to the change in the speed of the light as it goes from the air into the water, creating that illusion, the refraction or the bending of the light. So index of refraction, lowercase n, is defined by the speed of light in the vacuum, which is lowercase c, constant speed of light being 300,000 kilometers per second, divided by the speed of light through the material, lowercase v. So our index of refraction value can be calculated by dividing the constant speed of light by the speed of the light through the material. We can see that the index of refraction for a vacuum is 1. That's our baseline or our reference value. Air has an index of refraction of 1.003, which is slightly slower than 1, meaning that as air goes from as a light ray goes from vacuum to air, it is slowing down just a tiny bit. That light ray would slow down even further when it enters water because water's index of refraction or optical density is 1.33, and so on and so forth on this table. So Snell's law is an algebraic equation that we can use to describe the relationship between the angle of incidence and the angle of refraction as light passes through the boundary of two different media. In other words, there's a proportional relationship between the index of refraction of our first medium and the angle of incidence, and the index of refraction of our second medium and the angle of refraction. We can say that the index of incidence times the sine of the angle of incidence is equal to the index of refraction times the sine of the angle of refraction. Snell's law allows us to see patterns to how light rays behave and to use those patterns to infer or deduce properties of the medium. For example, light bends towards the normal. Let's look on this diagram. The normal is the line that is perpendicular to the two mediums. So here's our normal. And we can see that our incident light, or our light ray as it's traveling and hits the boundary between the two different mediums, should be traveling in a straight line, but it gets refracted or bent as it enters the second medium. This allows us to deduce that the second medium has a different optical density or in value compared to the first medium. And from that, we should be able to determine that the light is moving from a less dense to a more dense surface, and it's slowing down. In other words, because the light bent in towards the normal, we can infer that the N1 value here is lower than the N2 value here, that this is a less dense medium, and this is a more dense medium, and that the light is slowing down as it enters the more dense medium. We can see for this diagram the opposite behavior of light. As the Incident light hits right here at the boundary between the two medium. You can see our normal, always perpendicular to that medium boundary. And we can see that the light ray should have traveled in a straight line, as shown by the blue dots, but it actually bent and was refracted away from the medium, or away from the normal. Since the light ray was refracted away from the normal, we should be able to deduce that light is going from a more dense to a less dense surface. As it enters the less dense surface, it is speeding up. That's why it's bending away from the normal. And so our index of refraction for our first medium needs to be greater than the index of refraction for the second medium. It is key that we use our protractor correctly to measure our angles. So I just want to do a quick review about how we use our protractor. The first thing you should notice is if we're trying to measure this incident angle right here, we first need to orient the light ray that is coming in and make sure that our bottom of our protractor, the 0-degree angle on our protractor, is running along the boundary between the two mediums. And that the triangle, or the center of our protractor, is running along our normal being the line perpendicular to the boundary between the mediums. So that means this should always run through 90 degrees. To measure our angle, we're going to be measuring from the normal. So if we start at 90 degrees, we're going to count backwards. So this would be a change of 10 degrees, 20, 30. So this is 35, 36, 37, and 38. So our first angle is 38 degrees. If I want to measure the angle of refraction right here, I'm going to need to flip my paper upside down. And again, I want my protractor to run along the medium boundary, making sure that the middle of it is right at the normal, that perpendicular line to the medium boundary, and running through the 90 degrees. To measure my angle of refraction, I'm measuring from the normal out to the light ray. So again, I'm going to start at 90 degrees and count backwards. Here's 10, here's 20, here's 30, here's 40, here's 50, here's 60 degrees. My second angle is 60 degrees. So we're going to do 3 problems. 2 are going to be quantitative or mathematical, and then our last problem will be qualitative or more verbal to review Snell's law. So our first problem says light travels from ethyl alcohol with an index refraction of 1.36 into flint glass with an index of refraction of 1.65. What direction will the light bend? If the angle of incidence into the glass is 22 degrees, what would the angle of refraction be? And can we sketch the path of light as it changes medium? In what direction does the light bend? Well, we need to look at these 2 numbers. Our N1 value, our incident index of refraction for our incident ray, is lower than that of our index of refraction for our refracted ray or medium. So that should tell us that the light is going to bend towards the normal, because when N1 is less than N2, as our light crosses into the new medium boundary, it's going to slow down and bend in towards the normal. We can calculate the angle of refraction using Snell's law. So to calculate the angle of refraction, we're going to take our base equation, and to solve algebraically, we need to know 3 of 4 values. So we can see we have 3 values up here in the problem. We just need to identify what locations they go into. 1.36 would be our Ni value, or our index of refraction for our incident medium. 22 degrees would be the angle of incident, or the theta I value. And 1.65 would be the index of refraction for our second medium. And we'll be solving for theta r, or the angle of refraction. So our base equation should be 1.36 times sine of 22 degrees which equals 1.65 times the sine of the refracted angle we're solving for. Before we use our calculator, you definitely need to hit your mode button and make sure your calculator is in degrees, or you will not be getting the correct mathematical answer. So, to enter this equation into our calculator, we need to do the following. We're going to type in 1.36, hit the sign button, type in 22, close the parentheses, and hit enter. And we'll see that the left side of our equation becomes 0.509464967. So we now have resolved the left side of the equation. Now we need to look at the right. And we can see that the right side is 1.65 times the sine of the refracted angle. So we're going to take and divide both sides by 1.65 so that it cancels out over here. When we do so, we should get 0.3087767. So now our equation is our 0.3087667 is equal to the sine of the refracted angle. To solve for the refracted angle, we're going to need to divide both sides by sine. But to do this on our calculator, we can't divide by sine. We're going to use the second and the sine to the -1. Sine to the -1 means 1 over sine. 1 over sine is dividing by sine. So this is our way when we enter things on our calculator to divide by sine. So again, we'll take 0.30876647, and to divide by sine, we're going to do the following steps on our calculator. We're going to hit second and the sine button. You'll see that sine to the -1 pop up and a parentheses. Then we'll type in the 0.30876647, close the parentheses, hit enter, and you should get an answer of 18 degrees when rounded up to the tens place. So if we want to draw a diagram that represents all of the things we just solved for in this problem, we're going to need our two different medium. Here's our first medium, ethyl alcohol, with an index of refraction of 1.36. Here's our second medium, flint glass, with an index of refraction of 1.65. At the boundary between our two medium, we'll draw a perpendicular line, or our normal, and then we'll need to use a protractor to measure angles. Our angle of incidence should be 22 degrees away from the normal, and our angle of refraction should be 18 degrees away from the normal. All right, our second problem is going to be a slight spin-off of the first. Using the information given in the following diagram, calculate the index of refraction for the first medium. So we don't know our N1 value, but we do know the index of refraction for our second medium, and we know the angle of incidence as well as the angle of refraction. So again, for this problem, we're going to use Snell's law, but before we start, we really should think about what should this answer be? Should this be lower than, equal to, or higher than 1.33? That way we can verify and make sure that we get a good answer from our calculated value and we didn't make any mistakes. We can see that our light ray bent in towards the normal. So knowing that, we know that this substance, this medium, is more dense with a higher index of refraction. Thus, our N1 value should be a number less than 1.33. All right, let's take a second and solve this problem. We should have an x for N1, but our angle of incidence is 23 degrees, which is equal to 1.33, the index of refraction of our second medium, times the angle of refraction of 17 degrees. Again, to solve on a calculator, we're going to solve for both sides and then eventually solve for the x. So let's resolve the left side first. Take your calculator and find the sine of 27 degrees. The sine of 27 degrees should come out to 0.3907311285. Now let's resolve the right side. On your calculator, let's type in 1.33 times the sine of 17 degrees. You should get 0.388854367. To solve for x, we're going to divide both sides by 0.39073 value. And so x rounds to 1.00. It was 0.99 and it continued. If we round up, it will be 1.00. For our final problem, what can we infer about the index of refraction, optical density, and speed that light travels as it passed from medium 1 into medium 2 using the diagram to the right? So we can see this is our medium 1 and our medium 2. Our light is entering medium 1 right here at a set angle. It's getting bent as it enters medium 2, so we know we have different indexes of refraction because of that refraction of the light ray. And if we look at this diagram carefully, we should identify that this is our normal. The perpendicular line that runs between the boundary of the two mediums is our normal. And so our light ray is bending away from the normal. Here is its path if it continued in a straight line. And so we can see that it is being refracted away from the normal. If the light ray is being bent away from the normal, we should be able to use Snell's law in our pattern of light's behavior to identify its index of refraction, density, and speed in that second medium. So we should be able to say that N1 is greater than N2. In other words, N1 is more dense than the N2 medium. And that as light enters the N2 medium, it is slowing down, which is why it's being, as light enters the N2 medium, it is speeding up, which is why light is traveling faster and being bent away from the normal. I hope this podcast was helpful. Have a great